Hi, and welcome to the flipped instructional recording for 1.09 potential energy. As we get started today, remember you do need to update your science notebook slide. So if you struggle with note taking, listen for the parts of the lesson that I tell you to add to your notes. I will be covering the guiding questions, so be sure to jot down those answers as well. And don't forget, you need to create a slide or update your science notebook or page for each lesson that you work on in science. So as we jump in, sorry, my screen wouldn't pop up. We're talking about potential energy today. So have you ever wondered how a slim, lightweight projectile like an arrow can fly to its target with such force? Think about the moment just before an archer shoots an arrow from a bow. By pulling the string, the archer bends the bow back, holds still, and takes aim. At this moment, the string and bow are not moving, but they have the potential to move at any moment. The archer only needs to let go of the string, and the bent bow returns to its original shape, launching the arrow into the air. This lesson will explore a form of energy called potential energy and answer questions like, how do objects get potential energy, and how can potential energy become kinetic? There is a graphic organizer for this lesson as well. Again, I encourage you to use that document as part of your notes. It will help you understand everything about potential energy that you will need for your quiz and test. Here are the key words that you need to have defined in your notes. Elastic potential energy is energy stored due to a change in shape, a material that tends to stretch and return to its original shape. You've had energy before, it's the ability or capacity to do work. Gravitational potential energy is energy invested in a body by lifting it against the force of gravity. And potential energy is stored energy that is associated with the position of the object. So the main thing you need to remember here is where the object is has a huge impact on it being potential energy or not, or having high potential energy or low potential energy. So here are the guiding questions. We're looking at 7 for this activity, and I'm just going to open up a page to copy and paste those on so we can look at them as we go. So the first question we're looking at, what is potential energy and what are two forms of potential energy? So as we get into the lesson, that will be answered on the very first page. So it's the stored energy an object has due to its position or shape. So that is the answer to guiding question number 1. Objects that have potential energy do not have to be moving. However, they have the potential to move when a change in their position or shape occurs. Two forms of potential energy are elastic and gravitational. You will explore what these two forms of potential energy are. Along the way, you'll also examine real-life examples of potential energy to determine the role it plays in everyday life. And so the answer to the second part of guiding question 1 is elastic and gravitational. So we're ready to move on to page 2. The guiding question is, what is elastic potential energy, and give an example. So when a flexible object such as a bow or a spring is bent, stretched, or compressed from its natural shape, it stores elastic potential energy. So again, if you want to click here, you can get the definition. Make sure you have that in your notes, but it's also the answer to guiding question number 2. Elastic objects tend to return to their natural shape unless a force is acting on them. So when the shape of an elastic object is changed, it stores elastic potential energy, EPE, before it returns to its natural shape. Think back to the example of the bow and arrow. When the archer pulls the string back, the bow has elastic potential energy as it is stretched from its original shape. Now look at this mousetrap. Opening the trap winds the coil of the mousetrap spring tighter. The spring has to be held in place until in this unnatural shape by a small metal bar. At this point, the spring has elastic potential energy. When the trap snaps shut, the spring loses elastic potential energy as it returns to its normal shape. Consider another example, a rubber band. When does a rubber band have elastic potential energy? And that would obviously be when it is stretched beyond its natural shape. So question 2 says give an example. There are several listed in this reading, so just write one of those down. And as we move on to question 3, it says what is gravitational potential energy, and give an example. So objects can also store potential energy due to their position. Objects take on gravitational potential energy when they are lifted against the force of gravity to a position where they have the potential to fall. Gravitational potential energy, GPE, is a property of elevated objects. Imagine that you carry a basketball up a set of stairs and rest it on the top step. The basketball is not moving, but it has gravitational potential energy due to its position. With a slight nudge, the ball will roll down the stairs due to the force of gravity. This skateboarder entering the half pipe also has gravitational potential energy. As soon as she shifts her body, gravity will act on her and she will travel down toward the base of the half pipe. So you have the definition. You can click here if you need it again. And then there are several examples here that you can list as well to finish answering number 3. So as we move on to question 4, it says, how do you calculate gravitational potential energy? So just like we learned in the last lesson, there is a formula that you need to use. So the amount of GPE an object has depends on the object's weight, which you will see in newtons. Height will be in meters. So the height of an object is measured in relation to a reference point, such as the height above the floor. So here's the formula. PE, potential energy, is equal to the weight times height, or potential energy, right, equals weight times height. So you need to write that out, put it in your notes. If you can't remember W, remember we saw that W can be work, watts. So in this case, the W is weight. So if you need to write that out, go ahead and do that. So the formula for weight that you used in previous lessons is W equals mg, or weight is equal to the mass, which is in kilograms, times acceleration due to gravity, which is meters per second squared. So by substituting mg for W in the original formula, the formula for GPE can be expressed in this way. PE equals mgh. So the animation shows how PE is calculated using a ball with a mass of 0.16 grams that is tossed to a height of 4.0 meters above the floor. So the G is going to be a number that you're going to plug in that will be the same every single time. So we'll take a look at that in just a minute. So you have the mass, 0.16 kilograms. G is the gravitational constant on Earth. So if we're talking about on Earth, it's 9.8 meters per second squared. And then finally, we've got the height. And when you multiply those things together, you get 6.27 joules. So the answer will be in joules. Okay, so when you're solving these problems, you might want to write out mass, gravitational constant, and height. And you may also want to make a note that the gravitational constant on Earth is 9.8 meters per second squared. Okay, so number 4, how do you calculate gravitational potential energy? That's the formula. GPE is calculated with this M, G, and H. Okay, so as we go to the next problem, you're able to see that written out. So a ball being juggled has the greatest gravitational potential energy when it's at its highest point in the air, right before it falls back down to the juggler. Imagine that you could freeze that ball at this point. The acceleration due to gravity is 9.8 meters per second. So remember, that's a number that's going to be a constant that you're going to need to remember. It's kind of like pi, 3.14. just one that you plug in and remember. So if the ball's mass is 0.16 kilograms and the height above the ground is 4 meters, what is the gravitational potential energy? So this is what it looks like to plug everything into that formula. And then you're able to solve to get 6.3, and then putting in all the factors of kilograms and meters per second squared, remember, gives you an answer in joules. So you could just round that to 6.3 joules. All right, so if you review weight, remember that weight is a force determined by mass, the mass of an object multiplied by the acceleration due to gravity. Weight is measured in units of newtons. 1 newton is equivalent to 1 kilogram per meters per second squared. Remember that energy is measured in joules, so 1 joule is equivalent to 1 newton meter. You may want to put part of that, some of that, all of that in your notes so that you can remember that conversion. So on number 5, what does gravitational potential energy depend on? Let's click to the next page. So now try to calculate gravitational potential energy on your own. This bowling ball has a weight of 59 newtons. Its position 10 meters above the sidewalk on the roof of a building. Use the equation for PE, work times height, to calculate the gravitational potential energy of the bowling ball. Okay, so in that form, we would just see 59 newtons times 10 meters. So that would be 590 joules. Okay, so we are just multiplying those two numbers together pretty easily. So gravitational potential energy there. Since gravitational potential energy depends on weight and height, so that's your answer to number 5, weight and height. If the bowling ball was on a lower rooftop, its height was less, the gravitational potential energy would be less. If it were a tennis ball on the roof instead of a bowling ball, the tennis ball would have less gravitational potential energy than the bowling ball because it weighs less. So here are some potential energy concepts. Okay, you're able to go through and match some of these together to just get some practice. I encourage you to do that. Make sure you have them all correct. Take a screenshot and put these in your notes. So now there is a conversion between potential energy and kinetic energy. So this is going into the question on number 6, guiding questions. Objects at rest can have potential energy due to their shape or position. A change in their position, in their shape or position can set them in motion. Objects in motion have kinetic energy. Therefore, potential energy can be converted into kinetic energy. Look at this pole vaulter. His pole has kinetic energy as it bends during the leap. But when the pole is bent the most, it is not moving. At the moment when the pole is not moving, all of its energy is potential. This potential energy is converted to kinetic energy as the pole straightens out and springs the pole vaulter over the bar. When the pole is bent the most, does it store elastic or gravitational potential energy? So remember, it stores elastic potential energy because it is bent from its natural shape. So how is it converted to kinetic energy in the case of the pole vaulter? So it's talking about when the pole is bent the most, it's not moving. All of that energy is potential, and it's converted to kinetic as the pole straightens out and springs the pole vaulter over the bar. So that little part right here is your answer to number 6. And then it talks about what about in a roller coaster. So think about, let's see if this gives us an image for a roller coaster. Not really. So if you think about a roller coaster going up and down hills, right? So it's going really fast. It has a lot of energy to get the roller coaster up to the top of the hill. And at one little moment at the very top of the hill, it's got a lot of potential energy. And as it stops to change direction to go downwards, that's when the potential energy would be the highest. And then it's going to convert to kinetic as it starts going downward. So how does the potential energy change as the height of the starting point of the ball is changed? So we're looking at a simulation here. Here's a ball. Okay, so here the ball is at its highest point. That means the potential energy would be at its highest. It's not moving yet, so the kinetic energy would be at its lowest. As it rolls down, see if we can get it to roll. Okay, so as it rolls down, we know the kinetic energy is changing, right? It's getting higher kinetic energy. And then here it's changing direction up. And then so you can see in several places, wherever it changed direction from up to down, it's going from potential to kinetic or kinetic back to potential. So that's where you see the energy change. So here it says when the ball is placed at a higher starting point on the ramp, it has greater potential energy than when it's placed on a lower starting point. So how does the kinetic energy change as the height from which the ball starts down the ramp increases? So as it travels down, we know it's picking up speed. So that means it's picking up kinetic energy. And then how does the energy change from one form to another as the ball travels down the ramp? So when the ball is up here, remember at the top, it's got the most potential energy. So potential energy is high, kinetic energy is low. And then as it travels down here, we've got low potential and high kinetic because it's moving very fast. Okay, so that kind of gives you an idea on how it would relate to in a roller coaster as well. So for number 6, and then as we go through and answer, oh, here's another roller coaster. This could help you even more. So for many systems, you can predict how potential energy and kinetic energy will increase and decrease. Think about the motion of a roller coaster. As a roller coaster moves up a hill, it is being lifted against the force of gravity. Its potential energy increases as it climbs higher. Let's see, as it climbs. Okay, so when it reaches the top of the hill, the roller coaster stops moving for a moment. At this point, the kinetic energy is 0. All of the energy is potential. Once the roller coaster changes its position and speeds down the hill, its kinetic energy increases and potential energy decreases. So just as I explained. And is that elastic or gravitational? Okay, so here we're seeing an example of gravitational because it's lifted against the force of gravity. So that helps you answer, again, question 6. And then we get into 7 about talking about pendulums again. So look at the kinetic and potential energy changes of a pendulum. So as I play this, you can watch on the screen and see the PE and KE changing. So kinetic energy increases as the pendulum swings downward and decreases as the pendulum swings upward. Potential energy increases as the pendulum swings upward and decreases as the pendulum swings downward. So kinetic energy is the greatest when the pendulum is moving the fastest, and potential energy is greatest when the pendulum's position is highest. Okay, so remember, potential energy, its energy is based on the position of the object. So the higher in the air that the object is, the greater potential energy. And then kinetic energy is dependent on the speed of the object, right? So if it's moving faster, it's going to have more kinetic energy. Sorry, I almost said potential there. So more kinetic, the faster it goes. So we saw the animation and we saw the changes in the bars. And then you can just kind of compare. They're always opposite of each other. And so when is kinetic energy the greatest in the pendulum? And that is answered in here. So it's the greatest when the pendulum's position is the highest potential energy. And then kinetic is greatest when it's moving the fastest. So that answers question number 7 for you. So going now into conservation of energy, it says, watch the skateboarder as he rides on a half pipe. As with the example of the pendulum, the skater's potential energy increases as he moves higher up the half pipe. When his potential energy increases, his kinetic energy decreases. When the skater moves down the half pipe, his kinetic energy increases. And when his kinetic energy increases, we know that his potential energy is going to decrease. So notice that the bar for total energy remains constant throughout the skater's movement. This is because no energy is being created or destroyed. It's being converted from kinetic to potential and potential to kinetic. But the total amount of energy is conserved. Okay, so remember we talked about that law of conservation of mass. There's a law of conservation of energy as well. Friction, remember we talked about friction before. So in this and previous examples, we simplified the system by ignoring the force of friction. Friction is the force that resists motion. In real world, friction causes some energy to be converted into heat energy. So energy is going to be lost due to heat, right? Or added. So total energy is still conserved, but when it comes to heat and the conversion between, it becomes heat in the conversion between potential and kinetic. So this is something to put in your notes. I know there's a quiz or a test question that comes up about it too. Understanding that in the law of conservation of energy, if you're in a situation like this, you know, when wheels are going on a surface, we talked about there being friction. So friction is a factor as well. Some of that total energy becomes heat. So it doesn't just stay potential and kinetic. There is some of it that is converted to heat energy as well. So that's important to know. And finally, we are on the last slide. So this is a great review. But kinetic and potential energy are both forms of mechanical energy. You want that in your notes. Mechanical energy is always conserved when there is no friction or air resistance. That is an important sentence too. I would add that into your notes as well. And then it says, review the big ideas and practice making calculations with the gravitational and PE and KE equations. So going through and solving for all 13 of these would be a really great way to make sure you understand all the concepts that were in this lesson. And anything that you struggle with, I would encourage you to figure out how to work it correctly. Take screenshots of the question and the answer, or maybe write it down and write out how you solved it if it's one of the math problems, and have that in your notes so that when you take the quiz or the test, you have that to help you. So make sure you go through all 13 of these and make sure you're not just clicking and moving on, but that when you miss one, you spend some time. That's obviously an area of weakness for you. So spend some time making sure that you figure out how to understand it. You can see me in Help Lab if you have questions. But once you figure that out, then put that in your notes so that you have it to help you the next time you see it. And so with that, I know my PowerPoint slide started over, but we'll go through at the end. Look for a flip follow-up session in your Class Connect schedule. On this, you can come see me in Help Lab if you need extra help, and make sure you have a great day.